Hi, and welcome to another edition of Easy Theory. So let's do an actual example of the quicksort algorithm, which is another recursive algorithm that takes an array, finds what is called a pivot element, and moves all elements either to the left or to the right of this pivot, depending on whether it's bigger or smaller. So let's do an example of this. If I can spell example. All right, so let's let our array here be 1, 2, 0, 17, 8, 4, 9, 12. Okay, so I just made this array completely up. And one thing to pay attention to in the quicksort algorithm is that we are picking a so-called pivot element, but it does not matter which one that we pick. So let's just pick the element in the middle of the array, or at least close to the middle. But again, we can pick any element that we want to. So let's pick the one in the middle. So we can clearly see that the array size is at least 2, so we need to do some work. So let's pick, I don't know, let's pick 8. Okay, so my first pivot element is 8. So I'm going to write that down. So pivot is equal to 8. Well, the quicksort algorithm says move all elements that are smaller than this pivot element to the left side of the 8, and all elements that are bigger to the right of 8. Okay, the way that this is commonly done is we're going to scan through the array, and then we will do swaps if needed. So the 1 over here is smaller than the 8, so don't need to do anything. 2 is smaller than 8, don't need to do anything. 0 is smaller, don't need to do anything. So then now what we do is, well, okay, 17 is bigger than 8, so we need to move the 17 past the 8. So what I'm going to do here is I'm going to write 8 and 17 this way. Okay, so the 17 is to the right of the 8. So now what do? Well, and in fact, the way that you do this partitioning of elements smaller on the left and bigger on the right, you can do in any way that you want to. So for this 4 element, it's smaller than the 8. So let's put it right here and shift the 8 and the 17 over one position. There is a way to do this efficiently, but I'm not going to outline it here. Oops. The beauty of the quicksort algorithm is that you can achieve this in any way that you wish. But to get a good runtime, as we will be talking about in a few videos from now, it is actually important to get this algorithm, these pieces, as fast as possible. But it's just getting the idea across here. Okay, well then the 9 is on the right side, literally the right side, and then the 12 is in the right place too. So I'm just going to rewrite this to say that it's doing the partitioning. So yeah, it's doing the partitioning. That got cut off. I'll just call it a partition. Okay, so now what we need to do is, well, we need to recursively work with this piece and then recursively work with this piece, because the 8 is in the right place. The 1, 2, 0, and 4, they're not obviously in the right order, but they're in the right section. And similarly with these 3 over here. So let's work with this piece right here. So we have the array 1, 2, 0, 4. Let's just pick some middle element. Let's just pick 0. So pick 0. So that means that all elements to the left of 0 are smaller than 0, and all the elements that are bigger than 0 are to the right. Well, in this case, we just happen to be unlucky, and we picked the smallest element in the array. If you pick the biggest one, again, you'll have similar problems. So here, after partitioning, we're going to have 0, 1, 2, 4. So I'm going to mark this as after partitioning. Okay. So then what we have here is that this is the pivot, so we don't need to do anything with that. There's no left side of the array, so I'm going to mark that as an empty array. And we have the other side is having 3 elements. So again, we need to recursively go down on the left side because the left side is the first recursive call. So we recursively call on the empty array, and from the algorithm, we can see that if the length of the array is at least 2, then, if it's smaller than 2, we're not going to do anything. So here, in this recursive call for this empty array, we're not doing anything. So then we now go to this recursive call right here, which has 3 elements, so obviously we need to do something. So let's do 1, 2, 4. Well, that's the array I need to sort. So then what do we do here? Again, we're going to pick a pivot element. Let's just pick the middle one again. In this case, we happen to pick right. And after partitioning, we're actually going to have exactly the same array because this one happens to already be sorted. You could add a check to whether the array is already sorted before you do the partitioning. That actually doesn't change the runtime, as we will see eventually. So this is after partition. So then now we have the 2 pieces. So 1 here and the 4 here are the left and the right sides of the 2. So then now we do the recursive call on the left side. Well, that has 1 element in it, so therefore we don't do anything. And similarly, on the right side, it has 1 element, so we're not going to do anything. So then this recursive call is done. So that means that we have, well, it was clear already that we had a sorted array, so we didn't need to do anything. So then that means that this recursive call is done. And I should mention that each of these arrays are in place. So this is an in-place algorithm, meaning I'm not making new arrays. It's just I'm visualizing it as a new array. I need to modify the original array so that it becomes sorted, because that's what I'm trying to do. I'm trying to sort the original array. I could make a new array and then just copy and paste the sorted part into the first half right here if I wanted to, but it's typically done in place. All right, so let's do this recursive call. So we have here 17, 9, and 12. So let's just pick a pivot element. Let's just pick the middle one, which is 9, and we happen to pick badly in this case. So after partitioning, we're going to have 9, 17, and 12. If the array is kind of small like this, we could add a case to where we just brute force sort the array, because the array is like say 3 elements, then that's really easy. So if the size of the array is 3 or 2, then we just brute force if we wanted to, but I want to make this as general as possible. So we have 2 recursive calls, one that is empty and one that has 2 elements. So then this recursive call does nothing, as we saw before. Now let's do this one, which has 2 elements, so 17 and 12. So then now let's just pick a pivot element, which is, let's just say the 12 here, just as an example. Oh, I should say, so this is after partitioning, after the partition. And then now we're going to put the 17 on the right side of the 12. So we have 12 and 17. So this is again after the partition. And we have 2 recursives. We have a left side and a right side. The left side is again empty because there's nothing in this array that was smaller than 12. And we have the other recursive call, which is this 17. This first recursive call, again, does nothing. It doesn't change anything. And the recursive call on the 17 array, it does nothing because there's only one element in there. Okay, so then what we have here is this array right here, this 12, 17 will replace what this is right here, which is, and then so that in this array we have 9, 12, and 17. And then, so then over here in the original array, I'll have 9, 12, and 17. So the final array that we get is going to be just reading off the bottom recursive cases here. So we have 0, 1, 2, 4 for the first half that was sorted. Then the original pivot element, which is 8. And then the result of this array being sorted through these recursive calls, which is 9, 12, and 17. Okay, so that was an example of the quicksort algorithm. Put down into the comments if you have any better ideas of finding a better pivot element where we don't just happen to pick some pivot element that causes the rest of the array to be moved and it basically has roughly the same size array as before. Is there a better way to pick the pivot? And hint, there is. So hopefully that was interesting. Leave a comment down below for your thoughts on the quicksort algorithm, or if you have any other interesting examples. As always, please like and subscribe to the channel. It really helps us out. There are many other links in the video description if you want to contribute additionally, such as our Patreon, or a PayPal link, or a Discord server. And as always, I'll see you next time.